Welcome to G Fun Facts Online. Today we are journeying to the absolute bottom of the world to explore one of the most audacious scientific achievements in human history. We are going to Antarctica, but not to study penguins or climate change. We are going there to talk about a telescope that doesn't look up at the stars, but rather looks down into the ice, waiting to catch invisible messengers from the most violent corners of the universe. This is the story of neutrino astronomy and the IceCube Neutrino Observatory. To understand why we buried a billion-dollar machine in a frozen wasteland, we first need to understand what we are hunting. We are looking for the neutrino. In the world of particle physics, neutrinos are often called ghost particles, and the nickname is well-earned. They are the second most abundant particle in the universe, right after photons of light. They are born in the nuclear fires of the sun, in supernova explosions, and in the hearts of active galaxies. Yet, despite being everywhere, they are notoriously difficult to detect. Neutrinos have almost no mass and no electric charge. This means they don't interact with the electromagnetic force. They don't bounce off things. To a neutrino, a block of lead that is 1 light-year thick is as transparent as a pane of glass. They travel in straight lines across the cosmos, passing through gas, dust, planets, and stars as if they weren't even there. Right now, as you listen to this, about 100 trillion neutrinos are passing through your body every single second. You don't feel them, and they don't stop. This specific property, this refusal to interact with matter, is what makes them the ideal astronomical messenger. Light can be blocked by dust clouds. Charged cosmic rays are bent by magnetic fields, so we can't tell where they came from. But neutrinos? They point directly back to their source. They carry information from the deep engines of the universe, like black holes and neutron stars, that no other particle can escape. But this creates a massive engineering paradox. How do you build a detector for something that is defined by its inability to be detected? To catch even a handful of these high-energy particles, you need two things. First, you need a colossal target. You need enough matter that, purely by statistical chance, a few neutrinos will crash into an atomic nucleus. Second, you need that target to be transparent, so that when a collision finally happens, you can see the tiny flash of light it produces. You need a cubic kilometer of material. Building a water tank that size is impossible. But nature has already built one for us. The Antarctic ice sheet at the South Pole is over 2,500 meters thick. It has been built up over 100,000 years, layer by layer, compressing into a solid, ultra-pure block. At depths below 1,500 meters, the immense pressure squeezes out all the air bubbles. The ice becomes arguably the clearest solid on Earth. In this deep ice, blue light can travel for hundreds of meters without being absorbed. It is also pitch black, shielded from the sun and most cosmic radiation. This is why we went to the South Pole. Now, let's talk about the physics of how we actually see these invisible particles. We rely on a phenomenon known as Cherenkov radiation. When a high-energy neutrino finally slams into an atom of oxygen or hydrogen deep in the ice, it disintegrates the nucleus and creates a shower of secondary particles, like muons or electrons. These new particles are electrically charged, and they are moving fast. In a vacuum, nothing travels faster than light. But light travels slower through ice than it does through a vacuum. It is actually possible for these high-energy particles to travel through the ice faster than the speed of light in that medium. When this happens, they emit a shock wave of blue light. It is exactly analogous to the sonic boom created by a supersonic jet, but instead of sound, it is a boom of blue light. The detector, known as IceCube, consists of thousands of sensors frozen into the ice that watch for these faint blue flashes. By recording the exact nanosecond a photon hits each sensor, computers can reconstruct the event. If a muon neutrino hits the ice, it creates a muon. Muons are heavy and travel in straight lines, leaving a long track of light through the detector. These are excellent for pointing back to where the neutrino came from. If an electron neutrino hits, it creates an electron that scatters quickly, creating a spherical ball of light called a cascade. And if a rare tau neutrino hits, it creates a double bang signature, two distinct flashes that are the holy grail for particle physicists. Getting to this point wasn't easy. In the 1990s, a proof-of-concept project called Amanda showed that the optical properties of the deep ice were even better than expected. This paved the way for IceCube, a construction project of massive scale that ran from 2004 to 2010. The logistics were a nightmare. They had to drill 86 holes, each 2.5 kilometers deep. You can't use a normal drill for that. They built the Enhanced Hot Water Drill, a 5-megawatt beast that heated water to nearly boiling and pumped it through a high-pressure hose to melt through the ice. The drillers worked in shifts, 24 hours a day. Once a hole was drilled, they had a critical window of time to lower a string of 60 sensitive digital optical modules before the water in the hole froze back solid. They repeated this 86 times, deploying over 5,000 sensors. The final sensor was lowered in December 2010, completing the world's largest neutrino telescope. Since then, IceCube has fundamentally changed our understanding of the universe. In 2013, they detected two ultra-high-energy events affectionately nicknamed Bert and Ernie. These were the first neutrinos confirmed to originate from outside our solar system, carrying energies 1,000,000 times higher than anything produced by our Sun. This marked the official birth of high-energy neutrino astronomy. Then, in 2017, came the Rosetta Stone event. On September 22nd, a single high-energy neutrino triggered an automated alert. Within 43 seconds, telescopes around the world swung to look at the patch of sky the neutrino came from. They found a blazar, a supermassive black hole shooting a jet of particles directly at Earth, known as TXS 0506 plus 056. The blazar was flaring in gamma rays at the exact same time. It was the first time we matched a neutrino to a specific source, resolving a century-old mystery about where cosmic rays come from. More recently, in 2021, IceCube confirmed the existence of the Glashow resonance. In 1960, physicist Sheldon Glashow predicted that an antineutrino with a specific, massive energy would interact with an electron in a unique way. IceCube found an event that matched this prediction perfectly, confirming the standard model of particle physics using the cosmos itself as a particle accelerator. And just in 2023, researchers used artificial intelligence to filter through 10 years of data, separating the signal from the background noise to produce the first ever neutrino image of the Milky Way galaxy. It appeared as a ghostly, diffuse glow, confirming that our own galaxy is a source of high-energy particle acceleration. But operating this telescope is a human challenge, as much as a scientific one. While the summer at the South Pole is busy, the winter is a test of endurance. From February to October, the station is physically cut off from the world. Temperatures drop below minus 70 degrees Celsius. Fuel turns to jelly. Planes cannot land. A skeleton crew of about 40 to 50 people, known as winter rovers, stays behind. Among them are two IceCube operators, who keep the servers running in 24-hour darkness. To cope with the isolation, unique traditions have emerged, the most famous being the 300 Club. To join, you must wait for a day when the outside temperature hits minus 100 degrees Fahrenheit. You heat the station's sauna to plus 200 degrees Fahrenheit. You sit in the heat until you can't take it anymore, then you run naked, wearing only boots, out the airlock to the geographic South Pole marker. You circle it and run back. The temperature differential is 300 degrees. It is a brutal, freezing rite of passage that bonds the crew together. Looking ahead, science does not stand still. The success of IceCube has paved the way for IceCube General 2. This next-generation detector will be an order of magnitude larger, instrumenting 10 cubic kilometers of ice. It will allow us to detect 10 times as many neutrinos and pinpoint sources with much higher precision. For the absolute highest energy neutrinos, those that carry the kinetic energy of a tennis ball in a single subatomic particle, Gen 2 will add a massive radio array. This technology utilizes the Ascarian effect. When ultra-high energy neutrinos crash into the ice, the particle shower emits a pulse of radio waves. Since radio waves travel further in ice than light, we can bury antennas over a huge area of 500 square kilometers to listen for these radio clicks. Construction is expected to take about 10 years, ensuring the South Pole remains the capital of neutrino astronomy for decades to come. Neutrino astronomy via the Antarctic ice sheet is a triumph of imagination. We took a barren, frozen wasteland and turned it into a window onto the universe's deepest secrets. Every time a sensor flashes in the dark ice below the pole, it captures a story that has traveled billions of years to reach us. The ice is listening, and we are only just beginning to hear what it has to say.